Previously, we have been looking at momentum, and that implied that we were also looking at types of collisions, or collisions. And from your exercise on Tuesday, where you were playing around with and using the simulation, you looked at different types of collisions. There are basically three different categories of collisions. And the first one we are going to talk about today is called an elastic collision. In an elastic collision, not only is the total momentum of the system of objects that's colliding with one another conserved, but the kinetic energy is also conserved. Well, elastic collisions are not real common in the real macroscopic world. Billiard balls, pool balls, are a good approximation for an elastic collision. They do not deform, even temporarily, during the collision, but they do make a little bit of sound. You can hear that little tink when they hit. And so that carries away some energy, but not much. So we can approximate billiard balls or other very rigid objects like that colliding as an elastic collision. Now, air molecules are examples of things that undergo elastic collisions with one another, but that's not something that we see particularly. The next type of collision is an inelastic collision. In an inelastic collision, what happens is the objects involved in the collision deform, even if only temporarily. For example, like a tennis ball hitting a tennis racket. The ball squishes, the tennis racket strings stretch. They do go back to their original shape, but the fact that they deformed some during the process of the collision means that kinetic energy is not conserved. Some of the energy goes into the actual deformation of the object. What this means is that in the real world, most collisions, many collisions, are actually inelastic. And that means it can be very hard to try and analyze the motion of an object in an inelastic collision without having a lot of other information, like the direction that the objects are moving after the collision, how fast the objects are moving after the collision, or how fast were they moving before the collision and what angles were they going. And you have to have a lot more information. The final type of collision is called a perfectly inelastic collision. And again, momentum is conserved because it's always conserved, but kinetic energy is not conserved. But there's one saving grace for a perfectly elastic collision. In a perfectly elastic collision, as we saw, the two objects stick together after the collision, which means they have the same velocity after the collision. And this is really convenient. It decreases the number of things we have to have information about. So hopefully from the exercise that you did on Tuesday with the simulation, you discovered that kinetic energy was only conserved in elastic collisions. Well, our last topic for the semester is going to be torque and balance. And in order for us to understand how and why things balance, we need to talk first about center of mass. And center of mass is the point where all the mass of an object appears to be uniformly distributed around that point. Or equally distributed. I shouldn't really say uniformly because it doesn't have to be uniform. Or another way to think about this is a single point for an object where the force of gravity, i.e. the weight, can be thought of as acting on an object. Because while we've talked about the weight force pulling on objects before, we haven't really talked very much about how that weight force acts. Now, technically, if you have a large object, like a person, say, their mass is distributed over a fairly large volume. And it isn't that the force of gravity really only acts at one point. Gravity is actually pulling on all the parts of my mass. And yet, there is a way to locate a single point where it seems like the weight force is acting right there, the entire weight force for the object. And this is what we call the center of mass. Well, if you have an object with uniformly distributed mass, something like a meter stick, say, the center of mass is actually likely to be at the very center of the object, which is convenient. And if we were to take that meter stick, we could find that location for the center of the mass by putting it on a little triangular stand. We call this a balance or a fulcrum or pivot point. Well, the location where the meter stick touches that top of the triangle means there's going to be a normal force that acts directly upward on that meter stick. And if we have the center of mass directly over the top of that triangular balance, then the weight force will be acting straight down, and the normal and the weight forces will be acting basically along the same line. Now, they'll cancel each other out. What if we have something that's not a uniform distribution of mass like a person? Well, we can still do the same basic thing, finding the center of mass by letting the person get up on our little triangular stand. Well, you let the person get up on the triangular stand and they need to move around, move their arms and legs, bend their body until they're perfectly balanced. Once they are perfectly balanced, we know that the center of mass is then somewhere directly over the top of that triangular point, the pivot point. So it's somewhere along this pink line. Now, there's a lot of points on that pink line. So how do we narrow those down? Well, what you do is you let your person balance on this little pivot point again in a different way. They rotate themselves. Now, the pink line previously that we had drawn means that the pivot point, the center of mass of the person is somewhere along that pink line. But now with the person balanced in this new orientation, we also know that the center of mass has to be directly above the pivot point somewhere, so it's somewhere on that orange line. Well, the orange and the pink lines cross at that point where the green dot is. That green dot then must be where the center of mass of the object is. That is it. Now, as you can see in my little stick figure person that I've drawn here, it might be somewhere around the belly button of this person. In real life, the centers of mass of people can be higher than that or it can be lower than that. In men that generally have more upper body strength, the center of mass tends to be a little higher in the torso area. For women who often have lower upper body strength, the center of mass can actually be a little lower than the belly button in the torso area. So it can vary, but it's inside the body. Now, why is the center of mass important? Well, the center of mass is important because this is where the weight force that acts on a person can be thought to act. Right there, you can draw that weight force. And if the person were to get up on this balance in a different way, such that the center of mass was not right over the pivot point, well, that weight force then, acting right at the pivot point, would cause that person to rotate. And that's going to hurt. So it's possible for the weight force that acts on an object's center of mass to cause it to rotate. Well, let's go back to our perfectly balanced meter stick. With our perfectly balanced meter stick to start with, the weight force of the meter stick at the center of mass is right over the pivot point, so it's balanced all by itself. If I were to stick a small mass on the right-hand side of the meter stick, the weight force from this mass would cause the stick to rotate, and it's going to rotate in a clockwise direction. If instead I put the mass or a mass on the left-hand side, this is also going to cause the meter stick to rotate, in this case a counterclockwise direction. If I put them both together, one on the right-hand side and one on the left-hand side, and they are positioned just right, then I can get balance again. Well, how do we determine whether something's going to be balanced or not? Of course, you can do trial and error, or we can look at something called torque. Torque, for which we use the symbol lowercase Greek tau, is the result of a force that tends to rotate an object. So torque, mathematically speaking, is a force times a distance, or a length L. Now, previously we looked at a force times a distance when we looked at work. But when we did work, force times distance, that force and that distance had to be along the same lines. They had to be parallel. Well, in this case, the distance and the force must be perpendicular to one another. Well, what is the distance that we're talking about? Well, the distance is actually from the pivot point to the force. And let's look at an example. So here we have, from the previous page, our meter stick, where the weight of the meter stick acts at the center of mass and is right over the pivot. And then I put a little mass out here to the right. And so there's a force from the mass acting down on the meter stick. And that force from the little mass there is going to tend to cause rotation. Well, the distance is then the length from the pivot point to the force. And it has to be a length that is perpendicular to the force. So you can see how the length L and the force form a nice right angle. Well, when you do that, then you get the torque is equal to the force times the length. But in this case, it's actually negative. Because as it turns out, forces that cause clockwise rotation produce negative torque. Now we can do the same thing with the other mass here. The mass that we had on the left-hand side. And the distance L is from the pivot point to the force. And again, the length and the force are perpendicular. But now the torque produced, which is the force times the length perpendicular, gives us a positive torque. Because torques that tend to rotate objects counterclockwise are positive. Well, now let's see what happens when we look at both of these torques together. Well, if I have a negative torque on the right-hand side, one that tends to make it go clockwise, and a positive torque on the left-hand side, one that tends to make it go counterclockwise, if those two tendencies, one to rotate clockwise and the other counterclockwise, are the same, there will be no rotation. That means we have balance. Well, we can find balance by looking at the numerical values of these torques. And if they have the same numerical value, that means the same magnitude, we have balance. So let's put some numbers to this particular example. If I let my mass have a weight of 2 newtons and be a distance of 0.3 meters from the pivot point, then I get my torque as negative 0.6 Newton meters. Now, previously, when we were doing work and having a force times a distance, we called the Newton meter the joule. In this example, we will not use joules, but continue to use Newton meters because it's not the same thing, even though we end up with the same units here. Now let's do the force on the left-hand side. If we have the same weight and the same distance, we get a torque of 0.6 newtons. And so then we see down here that our two torques are balanced because they have the same numerical value. In the previous example, we looked at the two forces that were acting on the meter stick that produced torque, but we didn't consider the actual weight of the meter stick. And I want to look at it here quickly. The weight of the meter stick is acting directly through the pivot point, which means the length or the distance from the pivot point to the force is equal to 0. And this is why the weight of the meter stick itself in this example is not considered one of the torques. It's also why if you go and try to swing a door by pushing on the hinge, you can't really get it to open or close. But in the previous example, we looked at two masses that had the same magnitude and they were the same distance from the pivot point. Here I want to look at two masses that are not the same. Let's start out with a 3 Newton weight on the right side at a distance of 0.4 meters from the pivot point. And then we'll put another mass on the left-hand side at a distance of 0.3 meters from the pivot point. And if our meter stick is still balanced, that means that the numerical value for the torque on the right-hand side and the numerical value for the torque on the left-hand side have to be equal. In other words, the force on the left times 0.3 meters has to equal the torque on the right, which was 1.2 Newton meters. That means we can solve for the magnitude of the weight. And it turns out to be 4 newtons. So if we have different size forces acting on either side, they will have to be at different distances from the pivot point in order to make them balance. And we kind of intuitively know this. If you've ever been on a teeter-totter, you know that if you have people of different masses sitting on the seats and each of those seats is the same distance from the pivot point, you're not going to get a lot of teetering going on. One person, the heavier person, would need to move closer, or somehow the lighter person would need to move further away.